All right, IBAASL2. Today we're going to kind of revisit derivative applications because down the road we are going to have a test that has both derivative techniques and applications combined on one test. So today I'm going to show you two derivative application problems that involve all the derivative rules we have now. So there's, chain, product, quotient rule are on the table, and also e to the x, sine of x, cosine of x, natural log of x, all that good stuff. So first up, a company uses this equation for their cost of producing X items. The revenue in euros is for selling X items is represented by this function. So revenue is just the money that comes in. It's not like profit or anything like that. So it doesn't take into account the cost of the item or anything like that. So first up, find the cost of producing 300 items. Well, you're just going to find C of 300, which means putting 300 into the equation. So you get 100 plus 300 minus 0.01 times 300 squared plus 0.00006 300 cubed. And I believe this is 1,120 euros. So that's just how much money it takes them to produce 300 items. Now the next part says, find the marginal cost of producing 300 items. The marginal cost is using the derivative. And I'll do my best to explain why this is. The marginal cost is basically like, how much it's going to be costing per item to make 300 items. So, if you find the derivative, which finding the derivative of this is not that bad, we'll just do the power rule. So C prime of x, the 100 goes away and we get 1, and then 0.01 times 2, which is 0.02, minus 0.02 to the x power, and then bring that 3 out in front of that one. So that is plus 0.00018. So let me see, 1, 2, 3, 4. Yeah, that's what that means. X squared. Now, if we put 300 into the derivative, we get 1 minus 0.02 times 300 plus 0.00018 times 300 squared. I believe this is 11.2. Now, we have to explain what this means. That means it's like how much you're spending in euros per item since you made 300 items. Like if you only make 10 items in your cost function, like the cost per item would be different than making 300. So the cost per item is changing as you add more and more items to this. So when you take the derivative, it's almost finding like this instantaneous cost. It's like a cost right at 300. So 11.2 euros, the explanation for this. The way you need to think of it is that it's 11.2 euros to make the 301st item. Because the marginal cost is like how much you're paying per item for making 300 items. So if they were just to make, 301 items, then that last 301st item would be 11.2 euros to make. Now, find the marginal profit. Marginal profit is sort of the same thing as marginal cost, because the marginal part means that you're going to use a derivative. Oops, that's not what I wanted. So this is using a derivative again. But now we need the profit. formula. So profit formulas in general are profit equals revenue, which is all the money that comes in, minus the cost, because that'll be just the profit that you have if you subtract out all your costs. So our revenue equation, go back up here, is 22.8x minus 0.001 x squared, but then we need to subtract out the whole original equation, which is 100 plus x minus 0.01 x squared plus 0.00006x cubed. So now we need to simplify that and combine like terms. Well, let's see, the negative 100, let's just kind of go in reverse order since they are. So profit is going to be negative 100, but then the negative x would combine with 22.8, so that would be plus 21.8x. And then the negative 0.081, that wasn't 8, right? No, that's a 0. Gosh, my own handwriting get me. That would be combined with the positive 0.01. So we do 0.01 plus, no, minus 0.001 to get, yeah, that makes sense, plus 0.009x squared. So those two like terms are gone, and then we're just left with a negative 0.000406x cubed. So this is the profit equation. Now the derivative of the profit equation, we don't care about that negative 100. This would just be 21.8, and then we'll get plus 0.018x, and then minus 0.00018x squared. So we're figuring out the marginal cost of 300 items. So let's put a 300 in there. So we get 21.8 plus 0.018 times 300 minus 0.00018 squared. And I believe this is 11. So now we have to explain what this means. This is a marginal profit. So you'll get 11 euros more profit for selling the next item, the 301st item. I don't like how close that 11 got to the euros. 11 euros. There we go. Yep, that's what it means for the marginal profit. So remember, anytime you see the word marginal, you should be thinking derivative. Now, you guys, the average rate of change of a function f on the interval a to b is the slope of the secant line. You guys thought secants were gone, but they're not. So the slope of the secant line is b inside the function, and then subtracted by a inside the function, and then that's all over b minus a. This sounds complicated, but it's really just the slope equation. It's that slope equals change in y over change in x, which is the same thing as change in f of x over change in x, which is the same thing as rise over run, which, yeah, there's so many different ways to think of it, but that's what that equation is, basically. Now, the instantaneous, that word should always set off an alarm bell. Instantaneous, yeah, you should be thinking derivative when you see that guy. Rate of change of f at x equals a is the slope of the tangent line at x equals a, which is to say f prime of a. Yeah, f prime of a. Derivatives are just slope machines, so you're finding slopes of tangents when you put a into a derivative, and that's the instantaneous rate of change. So the average rate of change is like over an interval. It's like from A to B, like how the average change over that interval. Just repeating the words. But an instantaneous rate of change is more like the slope of a tangent. It's telling you what it's changing at one exact point, not over 2 points. Next example, over a month, the temperature in degrees Celsius in a pond is T of n equals 18 plus 12n e to the negative n over 3, where n is days and T of n is temperature. So find the average rate of change over the first 18 days. If you're just finding the average rate of change, that's the slope from day 0, or I guess I should say from n equals 0 to n equals 18. So to find the slope of that, you would put 18 into the function and then 0 into the function, and then that's would all be over 18 take away 0. So, I don't know if I want to write this all out. I guess I can. T of 18 is 18 plus 12 times 18 e to the negative 18 over 3. But then you have to subtract out t of 0. So this is 18 plus, well, that 0 is going to do away with everything, so it really doesn't matter. And this is all over just 18 minus 0, which is 18. And I believe this whole thing is 0.0297. Now, units on this, the average rate of change. The top, or the outputs, was the temperature, and the inputs were the days. So this is temperature over days. So the 0.0297 is degrees Celsius per day. That's how much it changed on average over the first 18 days. Now the next part, find T, you know what, I'm going to scoot this mid-video. Behind the scenes with Mr. Jolly. Okay, to find the derivative of t, I see that this part we don't care about. It's just going to go away. But this part here is interesting because it's going to be a product rule. It's 12n times e to the negative n to the e to the negative n thirds. So that's going to be a first d second plus a second d first. So t prime of n is going to be equal to first, now d second. Now d second, the derivative of just this part is going to be a chain rule. So derivative of the outside with the inside the same, but then times the derivative of the inside, which is negative 1/3. So that was first d second. Then we have to do plus second d first. So second, just unchanged, and then d first is just 12. Now, can we clean this up? I think we can clean it up a little bit, you guys. One thing I'm noticing is that this negative 1/3 times 12 is going to give us a negative 4. Also, should we pop things into the denominator? No, they do not. Okay, so let's just leave it like that. So this will be like negative 4n e to the negative n over 3. And then the back half you really can't change too much. It's just this. So that's the derivative. Find the exact value of the instant radius of change on day 18. Well, that's just going to be putting 18 into our derivative. So t of 18 is equal to 12 times 18 e to the negative 18 thirds. No, sorry, I'm reading the wrong line. Come on, Jolly, pull it together. Negative 4 times 18 e to the negative 18 thirds plus 12 e to the negative 18 thirds. So if you crunch this all out, you can get an exact answer. In fact, let's show some steps here. Negative 4 times 18 is what, 72? So this is negative 72e to the negative 6th. And then this is 12e to the negative 6. Now they both have endings of to the negative 6, so they are like terms. So if you add those two together, you get negative 60e to the negative 6th. Now this is degrees Celsius per day. That's the instantaneous rate of change. If we want to compare that to our answer in the first part, we could decimalize that and say that this is negative 0.149 degrees Celsius per day. Now, is this interesting? Not really. I mean, this is the average temperature change over the first 18 days, and this is the instantaneous temperature change on the 18th day. About a pond. I don't know why we care about the temperature of this pond. Maybe there's something special in the pond that we care about the temperature that it's at. But yeah, not the best real-world example, but the math is kind of interesting. A little product and chain, a little instantaneous, a little average, secant stuff. All right, guys, this is the first two of like a bunch of optimization examples we're going to throw at you. But just for today, just these two. Continue working on these problems and ask questions if you get stuck.